can see people filtering in. So I'm going to make a start. Good afternoon and welcome everyone to this July version of Wednesday with Wing. We're very lucky today to have Mark Cottrell speak for us this month. Just before we get into the presentation, I'll just put in a few housekeeping rules. So all the attendees, your mics and your cameras will be turned off. And if you have any questions, please put them in the Q&A or the chat if that's easier for you. At the end of Mark's presentation, we'll have an opportunity to have a bit of a discussion in which you will be able to turn your cameras on or mics on should you want to or like ask a question yourselves and have that bit of discussion go on. This talk is being recorded, just to put that out there. Great. So I'm going to introduce our speaker. So Dr. Mark Cottrell is the Technical Director for WSP and a seasoned multidisciplinary subsurface professional. He offers expertise in various industries, including geothermal, infrastructure, nuclear waste, and mining, whilst also serving as Global Technical Director of Geoscience and Fracman. His technical focus is on geomechanics and rock mechanics with experience in both natural and man-made materials, and he leads technical consulting projects across multiple disciplines, promoting collaboration with colleagues and stakeholders. So I'm going to pass over to you now, Mark. Thank you.
Hi there. Welcome, everybody. Thank you for having me here today. So the presentation that I have here today, it introduces a study where we were evaluating the geothermal potential of hot sedimentary aquifers in the Denver Basin in the United States. The project is the result of a collaboration between WSP, the end client Geothermal Technologies, and Johns Hopkins University. So it really emphasizes the multidisciplinary expertise that goes into these types of studies. This slide really sets the stage for understanding how advanced modeling techniques and approaches, such as those in Fracman that we're going to see today, can be applied to geothermal resource assessment. Okay. In terms of motivation, this slide outlines the rationale for adopting geoscience tools to support the energy transition. So from hydrocarbons to greener alternatives. It also highlights the evolution of some of the tools that we apply to these types of problems. So for Fracman, originating in the late 1980s, to its current application in the deep geothermal reservoir space. This slide also contrasts the traditional application areas with new ones, illustrating how the workflows that we apply must be continuously innovated and repurposed to meet the emerging energy challenges. This slide provides a brief overview of geothermal energy advantages compared to other renewables. It emphasizes the potential for safe, sustainable, and reliable long-term energy production. It also highlights its ability for providing baseload power, unlike other intermittent sources like wind and solar. The focus on hot sedimentary aquifers explains how these formations with their high porosity and their high permeability can still enable efficient heat extraction through fluid and rock matrix and fracture flow. These aspects are there to support favorable economic and long life of these types of projects. The modeling workflow philosophy that we employ is presented here. It illustrates a pretty simple, but actually a structured approach from developing a geological conceptual model through to the parameterization, and then finally resulting in an application that we can use for decision making. Key considerations include the geological, the hydraulic, and also the geomechanical descriptions, as well as factors like cost, efficiency, regulation, and environmental impacts. This holistic framework is there to ensure that the efforts that we put into these types of projects are comprehensive and actually aligned with practical project needs. This next slide is really there to give us a very brief introduction into the Discrete Fracture Network method, the DFN method. It's there to be a versatile toolkit that's applied across multiple industry sectors. And by integration of the philosophies and the workflows from these various sectors, it allows us to leverage that cross-sector experience and expertise to address complex challenges that we do encounter in the geothermal space. This multi-sector cross-fertilization approach, not only does it enrich the methodology that we apply, it also enhances its robustness and applicability to energy projects. The focus on this slide is just to highlight some of the continuous innovations, highlight some of the aspects of resilience that we have to include in our toolkit. Key technical areas include accurate geological description, fracture networks, matrix descriptions. We need advanced geomechanical modeling that can bridge large-scale descriptions all the way down to laboratory scale descriptions. Similarly, for the fluid descriptions that we need to use in these geothermal assessments, we need to have sophisticated characterization to go alongside sophisticated simulations. The integration of high-performance computing, data analytics, and machine learning enable us to develop bigger, better models that include greater detail, and ultimately allow us to improve our prediction capabilities and therefore make better decisions. The next few slides are very much focused on the actual simulation case that we did for the Sedimentary Aquifer project. I'm going to give a few bits of information around data, workflow, and actually what kind of results are we getting out that we can use to actually get better understanding of these types of projects. This slide gives a very high-level overview that we use for these types of approaches. It describes the types of data, the types of integration that we look to perform with that data, emphasizing key stages such as loading, visualization, characterization, and analysis. It's a systematic approach that ensures that we can amalgamate diverse data sets seamlessly. It allows us to enable accurate modeling and supports informed decision-making for geothermal reservoir characterization. So the particular piece that we're interested in the analysis in this project, it's all about the design of the wells. How can we actually position those wells such that we have optimal contact with the reservoir? It's also about, well, how can we operate this project such that we have demands of power and longevity that can be continuously met. Types of data that's required for these types of geothermal reservoir characterization projects is summarized here. There's a lot of data here that is very familiar. There's nothing outrageous or unusual here. These are the types of things that we broadly look to characterize in all of our subsurface projects. Some of the descriptions that we need can be really complicated. Some of those descriptions can actually be quite easy and does not necessarily rely on detailed input data. Understanding of these properties for each of the reservoir layers is crucial for building reliable models such that we can predict reservoir behavior, fluid flow within the reservoir, and also understand the heat extraction that is possible from those reservoir rocks. This slide, just to give a bit of a grounding as to where the project is taking place. So this is the Lion Sandstone, the inset map. The inset map on the image, the green area is the Lion Sandstone, so you can see quite clearly it's a big reservoir unit. It's a big formation. So we've got Colorado, Nebraska, Kansas. It's spanning multiple states in the US. So we've got something that's 500 kilometers by 600 kilometers. It's a really big area. We can see from the image here, it has some favorable characteristics that we want to exploit. The matrix descriptions are indicating really good levels of porosity and permeability. These things allow fluids to flow through the rock. That flow potential is further supported by the presence of discontinuities in the rock. So making use of natural fractures, using those natural fractures to actually provide the hydraulic pathways in the subsurface. And if we can understand the presence of these things, we have a means of evaluating the reservoir performance. We have the means of using that information to help us design better wells such that we can contact the reservoir efficiently. Okay, this slide gives us a bit of an insight as to, well, what does the model actually look like? What is the process that we followed in constructing that model? The center picture here is basically the DFN model. So this is the natural fractures that we built over an area of about a square kilometer. Every one of these fractures is characterized using well data that is available. So it could be standard wireline data, standard geophysical logs, fracture image log data, such that we have in the lower right corner here, where we have information that tells us about the intensity of those discontinuities. Also helps us inform the orientation of those discontinuities. It is a former area of shale gas development. So the shale gas reservoirs were beneath the Lion Sandstone. So there were a lot of wells that went straight through the Lions to look for the shales underneath. But in most cases, we did have wells that provided data for the Lions. So lots of data. There's also seismic survey data, such that we can actually start identifying facies, also the layering of the reservoir, and then also other major contributing features, so things like faults. So we can build those things into the model. There is well test data, so we can start understanding well, what is the flow potential in those units. Can we use that to improve our understanding of what the geothermal reservoir will behave like? Okay, so a bit more detail about the modeling. This slide gives us some details on the configuration and the simulation strategy. It describes the use of horizontal wells. Those horizontal wells are typically up to about 1,000 meters in length in terms of their horizontal component. They're offset from one another somewhere in between 500 and 1,000 meters. The spacing of the wells is quite an important design measure. We want to have the wells close enough that we guarantee conductivity, so a connection between the well locations, but we obviously want them far enough apart such that we're getting the best thermal contact from the heat that's available. If the wells are too close together, there's just not enough time for the heat to transfer to those circulating fluids. The integration of the DFN description, so the discontinuities, is coupled with regular continuum descriptions that we use for the thermal description, can also be applied for the geomechanical description. So it's very much a coupled simulation approach that is genuinely supported by log data, seismic data, to actually provide a robust reservoir engineering model. So I try and advance it. So just talking about that data and the workflow. So we've got a reservoir model, we've got some seismic data, we've got some well log data, so we can see the fracture data on the wells. I advance that. We turn that into our DFN model. So we're describing the pattern of fractures in the reservoir units, and we're then taking that discontinuous description, that discontinuous DFN description, and turning it into a grid-based conventional reservoir model, so a continuum description. The next few slides, we're basically going to look at some of the results that are coming out of these simulations. So we can see the two wells. We're injecting fluid into the lower of the two wells. The injection of that fluid is at 50,000 barrels a day. So that is really, that's a really high injection rate, and it's the ability to inject and produce at such high rates that makes hot sedimentary aquifers work. Whilst we may not have the temperature profiles that we see in some of the volcanic based projects where you've got fluid temperatures of 150, 200 degrees Celsius, we can accommodate slightly lower fluid temperatures here because we're able to circulate the fluids at a much greater rate. So actually the power levels are still significant for power generation. So on our two wells, we can see the injector, the fluid rises at the producer well in the upper of the two. The drawdown introduces a reduction in the pressure. We can see the asymmetry between the two production profiles. So we've got the fluid pressure. We can also see for the reservoir fluid temperature. So we can see as we start injecting fluids, we can see that temperature decrease, that plume of cooler water gradually grows with time. So we can see it growing over a 16-year period here. We can see how it actually connects up with the producing well. If we start looking at, well, how can we use this information to optimize our design? This slide just gives an indication of the pressure profile for different well spacings. On the left, where the laser pointer is, this is the buildup. So this is on the injector well. So we can see the pressure buildup. we can see the pressure buildup is accompanied by the drawdown on the production well. We can see these vertical lines here are two different well spacings. So we can see, whilst the overall magnitudes of buildup and drawdown may not change that greatly for these cases, if we actually start spacing them out, are we going to see impacts in terms of the temperature? So just take a look at the temperature data. So we can see these three curves are basically the drawdown that we see. So this is the thermal drawdown that we see as we change the well spacing. As we start putting our wells closer together, whilst we're increasing the connectivity, so the likelihood of hydraulic connectivity, we can clearly see there is a really big impact in terms of, well, how quickly does that injected cold, cooler water, how quickly does it actually reach the production well? So we can see, so this upper line is at a 1200 meter well spacing. We can see the thermal drawdown is pretty minimal. The center lines here are an 800 meter spacing, so we can see we're getting a degradation of maybe 7 or 8 degrees. And if we actually make those wells closer again, so only a 600 meter spacing, we're actually taking quite a lot of temperature out of the system, especially after 20 years of operation. One of the things that is really important for the operation of these types of systems is, well, how much fluid are we actually touching with our system? If we've got a certain acreage, could we actually put multiple systems, multiple operations in that reservoir? So instead of having just a single duplet, as we've considered here, could we have multiple duplets spread around the license area? The modeling that we have employed allows us to evaluate well, what is that footprint? The harvest reservoir volume is one of the key metrics for assessing that, and it's basically evaluating the footprint of the waters of various years of operation. We do that primarily using a particle tracking approach, and what that means is when we inject fluid into the injector, we monitor where that fluid goes, and that monitoring, as I say, is done using particle tracking. So basically, if you think of like ping pong balls that get carried with the fluid as it moves in the subsurface, so we can understand where those particles actually end up after certain durations of operation. We do a similar thing, but actually in reverse, for the producer well. So we can see the producer well on the left here. In that case, we simulate, well, we know the particles end up at the producer well, but we integrate backwards in time to actually find out, well, where did those particles originate? Where did they begin? And using those particle tracking approaches, we basically get these envelopes or profiles that actually tell us, well, at this point in time, this is the water that has been produced. It also tells us, importantly, is this fresh reservoir water, so water that has been untouched before, or are we actually producing water that has been injected previously? I'll talk a little bit more about that on the next slide. So summarizing that harvested reservoir volume, we can see how it evolves over time. You can see it grows, and then actually the growth of it tends to flatten out. So we're not actually going beyond a certain shape. We reach that maximum and it then basically continues. So in that, once you reach that point, the injected pool of water is actually water that has been injected previously. The chart on the right here, so the composition of the fluids that are produced, we can see how our injected water increases. For this case, we can also see over the 20-year period, we're still producing, a good volume of natural reservoir water. So actually, the longevity of this operation could actually be extended out quite significantly beyond 20 years. If we think about the other end of things, so what happens when we stop producing? One of the key things we've needed to address through this project is, well, is it really green? Is it really renewable? So we've used these types of approaches to assess, well, how quickly will the subsurface recover? If we think about recovery times for other geothermal systems, so high enthalpy, so the multi-phase deep geothermal systems that like Forge, where we've got steam and water. In those cases, we're looking at several hundred years. For this case, so a hot sedimentary aquifer approach using a doublet system, we're probably looking somewhere in the region of 100 to 300 years. And then the third case I have here to fully cover it is, if we think about district heating and ground source heat pumps, those times of recovery periods are probably in the order of 30 years. So they're really quick. So these resources, these geothermal resources, can definitely be considered renewable in terms of their recovery timescale. Okay, just a summary. So I presented how we need to adapt our workflows, how we need to integrate our workflows for describing hybrid, discrete, hybrid continuum geologies. It very much requires integration of the geology, the geomechanics, and the reservoir engineering. This allows us to provide really good world-leading support to deep geothermal reservoir characterization and development. These types of approaches allow us to evaluate the reservoir potential. They allow us to evaluate the requirements around the injection and producer wells, guiding key decisions such as well spacing, operational rates, so high rates such that we can actually maximize the production but without damaging the integrity of the reservoir. These types of approaches, they're not new. They've been applied for many years in the energy industry, in the oil industry, and they're now repurposing for the renewable system. The calculation of the harvested reservoir volume is really key. It's a novel approach. It allows us to actually quantify what is the footprint of our geothermal system. It allows us to understand questions. Well, where does the injected water go? Where does the produced or the recovered fluids come from? With that, I'll finish here. I'll open the floor to any questions. Simran, over to you.
Thank you so much, Mark. It's been really great to listen in and understand how that workflow contributes to hot sedimentary aquifer development. Okay, so I think now's the time where the attendees will have the option to turn their cameras on or ask questions themselves. I can see there are a few questions in the chat. And I guess I put one in as the first one, so I'll go with that one.
Okay.
I was interested in how sedimentary facies can actually contribute to fluid flow in these deep sedimentary aquifers.
I suppose in the case of the lions, the matrix, the matrix porosity is 25% plus. The permeabilities are in the orders of hundreds of millidarcies. The natural fractures, just further enhance that permeability potential. They're just really great, really great rocks for flowing fluids. So, if we think about the UK, for example, there's actually been some news in the media just in the past few days about the Sherwood sandstone in the UK and its ability to be used for geothermal. So, sandstones, yeah, you have a lot of potential in those types of rocks.
Okay, yeah, great. And just to follow up on that, so am I right in understanding that the this model that you've created, the Denver Basin, have they actually, is this a functioning geothermal system, or have they done any in situ tests?
There are in situ tests that have come from legacy oil and gas exploration in that part of the world. In terms of the geothermal operations, there is a project program where drilling of new wells is ultimately required to actually get in, to get the wells in the in the reservoir interval that we need them to be. So there is a lot of data. It is legacy data. To follow that up, yeah, we need to move to new wells actually targeting the lions.
Okay, understood. Okay, great. So the next few questions, I think there were two that related. So one is why do you use a approximate 25-year design life? And I guess that's related to recovery times, which Hester has asked about.
Economics is the simple answer. These types of projects need to produce a necessary power level for a necessary time period to actually, to make them stack up. So 25 years is what, it's what the accountants deemed as an attractive possibility for actually making these projects viable.
Agreed. And yeah, you did present the slide on the sort of renewable timescales of
Yep.
geothermal as well. So the accountants maybe need to know that you're looking at 100 years. So sometimes.
Yeah. I think for this particular case, the operational time period or the operational time period that's possible at these locations is probably beyond 25 years, probably more like 35 years. But then, after 20 years of operation, you have other issues to deal with. Do you have to renew your plant? Are there issues with the with the actual infrastructure around it? So whilst the heat is still there in the subsurface, do you have to clean your wells, for example, because of scaling issues? Do you have to renew your turbine that generates the power? So there are other things, but based on that 25-year period of saying, well, the economics works, I think the slides here show that geologically, it definitely does work.
Excellent. Of course, there are many considerations on the, I guess it's called upstream. Is it called down? Yeah, upstream side. Yep. Hester asks, have you looked at multiple wells extracting from the same reservoir and how this affects lifetime recovery? Could this be used to develop policy, e.g. how many geothermal wells are allowed in one reservoir?
Yes, we have, and I think that reinforces the need to actually be able to size this harvested reservoir volume. Obviously, if you have, two pairs of wells where the harvested reservoir volumes overlap, you basically got you're going to have a connectivity between different groups of wells. We've also been using the tool for evaluating the interaction between, well, do we require one injector for every producer, or is it more efficient to have multiple injectors positioned around the producer? So there's lots of questions that you can ask and ultimately answer using these types of analyses. And yeah, I think they can be used to demonstrate and even guide, well, what should the policy look like when it comes to well spacing, when it comes to positioning of the wells, even, if there are geological structures in the subsurface, how close can or should we get to those? So the approach can definitely answer those types of questions, yes.
Great. Another question from Hester is a big question. How do you incorporate subsurface uncertainty into the software?
Okay, so the approach that we have here, we're not looking to do one model, one simulation, one answer. That is just geological suicide. So the modeling approach that we have here, the models that we set up, the way we parameterize them, they're basically described using a combination of deterministic descriptions, but also stochastic descriptions. So when we say deterministic, we're including things that we know this bit of rock has this type of data. We know exactly what it looks like. We don't want to change it. Now, if you think of well data, well data, we have a log. We know what the properties are along that log. If we go 30 centimeters away from the well, we're into the realms of uncertainty. So what we do when parameterizing our model is we build stochastic descriptions that can be applied away from well control. So what that allows us to then do is to say, well, we know this property has this type of statistical description. So it could be, just some kind of distribution that says, well, the porosity or permeability is sampled from a distribution that we've created from observed data. And what that allows us to do is actually produce multiple realizations of the same model. So each realization of the model is statistically valid, but every realization of that model is individually unique. So for these types of projects, we may do 100, we may do 1,000 realizations of the same model simulation. And then we can use the results from those models to probabilistically predict, well, what is the outcome. So it could be, for example, well, 90% of the time we see the production temperature drop by 5.4 degrees. So that probabilistic nature allows us to actually be confident in terms of what the model is saying. We're not just pinning our entire project on the result of one simulation. And that one simulation is an individual case that did or did not work. We're actually doing multiple cases, and we look to then actually probabilistically say, no, based on the results, based on these statistical inputs, this is the range of outcomes that we're getting, and this is the likelihood attached with those outcomes.
Excellent, thank you.
Okay.
Yes, I think that answered the question very well. We've got a few more come in. So Leah Swan says, really interesting presentation. Thank you. You have lots of data available in this Denver Basin example. I was wondering how you would approach a similar problem in an area with very limited data.
Okay, so I think broadly linked to my previous answer. So because we're describing things stochastically, we can use that concept of multiple realizations to actually identify what matters. So if you think about the data that we plug in, we may have a list of 10 or 20 things. The reality is, with these types of subsurface projects, some of those bits of data will matter a lot. Some of those pieces of data will actually not influence all that much. And these types of modeling approaches allow us to test the influence of those models. So, what we may say, in a case where we've got very limited data, we may want to say, well, actually, let's keep everything equal as a best guess, and let's just parameterize or parameter sweep, I should say, the thermal conductivity, for example. How big a difference does that make? And we can actually run these groups of simulations where we individually, or maybe in a small group of parameters, vary their value such that we can test their influence. And what that allows us to do is actually, firstly, it allows us to actually put some guidance into future data acquisition. But it also allows us to use analog data where maybe we're in the right ballpark, but we're not actually all that close. So I would say, most of the projects that we do these days, we never have everything in the subsurface. So, for the data that we're missing, using analogs, using some kind of parameter sensitivity for the values that you're really uncertain of, actually allows you to build a pretty robust understanding of the subsurface.
Great, I hope that answers the question well. So Hannah asks, why did you model with horizontal wells and not vertical wells?
Purely because of contact. If you think about these reservoir layers, these sedimentary layers could be, they could be quite thin. In this case, they're the tens of meters. If we have a vertical well going through that formation, and let's say the formation is 10 meters thick, we've basically got 10 meters of rock to actually provide the production. If we have a horizontal well, as we've done here, we have up to 1 kilometer of well that can actually be used to produce the fluids. And I think where this becomes really important is when we take into account, well, we're trying to inject and produce fluids at really high rates. 50,000 barrels a day is a huge rate. If we try to inject that amount of fluid in a small interval in a vertical well of say 10 meters, we're basically going to jack up the fluid pressure so quickly that we would almost certainly hydraulically fracture. By doing it in a horizontal well, we're able to distribute that volume of fluid over a much bigger area, so the pressure increase is much less. If we think about the production well, extracting 50,000 barrels a day over a 10-meter interval, we're going to have to be sucking quite hard on that well. And what the implication of that is, in these lower strength sandstone formations, the strength of those rocks are pretty low. If we start extracting small intervals at really high rates, we basically have operational issues. So things like wellbore sanding become more of an issue. So, if we're taking sand out of the producing interval, we're going to have integrity issues. We're going to be producing lots of sand at the surface that probably doesn't react all that well with the plant equipment. So similarly, if we have a horizontal section that is much longer, we basically have a distributed lower rate that each unit of rock that contacts that production interval. So that is really simple. Having the horizontal well just gives us a bigger contact area, such that we don't have to be so severe in terms of injection and production. That's it.
Thank you.
Okay.
Okay, great. And another question from Hannah. Was the data used collected for this specific project, or was it legacy data, I think?
It's primarily legacy data. There are hundreds, if not thousands, of shale gas wells in the Denver Basin. Some of those are becoming, the actual production of those wells is rapidly declining. There are also, lots of exploration wells. So there is an awful lot of data that, just exists. And, when I say legacy, I'm talking about, good quality wireline data that was acquired in probably, within the past 20 years. So it is good quality data. It's not, it's not sort of historical paper logs that were acquired in the 70s. We're talking about really good quality data that captures most of the lions, but was actually primarily acquired to target the shales in the deeper levels of the basin.
Great. And actually, I just had a question in relation to this. So in the US, I'm wondering, in your experience, do you think that they are actively now going to be looking to repurpose these old oil and gas or shale oil wells, or is this still like a topic that's being decided by by various factors, or is it something that you've seen as a positive thing that they're pushing?
I personally think it's a positive thing. I personally think some of the historical oil and gas hotspots in the US are ripe for geothermal. The Denver Basin being one, West Texas moving into moving westwards into the likes of California, for example. I think it comes down to being able to have the wells in the right place. So you may be able to repurpose an existing well and recomplete it to actually, to actually target the formation that you want to circulate these fluids in. But I would say you will be pretty lucky if actually the well, the duplicate well, the other well that you need to inject it, exists in the right place. And that there have been various studies over the years looking at repurposing wells. So if we think about in Nevada, for example, a conventional oil and gas location, there were wells that were producing. There were studies that were undertaken to see, well, could they actually repurpose an existing producer to a geothermal producer? Could they repurpose another existing oil and gas producer into a geothermal injector? And it's about ensuring, well, actually, can those wells hydraulically connect? There may or may not be a natural connection. And I think it's those kinds of obstacles that probably prevent us right now saying, well, we've got 1,000 oil and gas wells here, let's repurpose all of them. It's a question we can answer. We can certainly make use of the tools that we have out there for answering those types of questions. But as of today, those still remain unanswered.
Yes, okay, thank you so much. I actually had another question based on the method or the workflow, and I put it in here. So I've come across the term upscaling quite a lot when it comes to modeling, and I just wanted to know, in this case, does upscaling mean of parameters such as permeability, thermal conductivity? Is it a spatial process in which you extrapolate properties to areas where you don't have data?
Okay. Right. Upscaling probably means different things to different people. If you talk to a geologist, for example, upscaling could mean exactly as you describe it. So basically taking data that you have at some known locations and propagating it away from those locations to sort of fill in the gaps. The second description of upscaling, which is probably more aligned to sort of a reservoir engineering terminology, it's about how do you integrate secondary porosity and secondary permeability into the primary porosity and permeability description. So what that basically means is, well, how do we incorporate the fracture contribution and combine it with the matrix contribution? So that workflow is also called upscaling. There are very standard numerical approaches for doing that. So you can do upscaling for flow. So it could be, well, what is the extra permeability and porosity that the fractures bring to the matrix? It can also be geomechanical as well. So it could be, well, we know what the geomechanical description of the rocks are in the laboratory. we have these little core plugs that we do tests on. We can figure out its stiffness. We can figure out its strength. How does that change when we start looking at the field scale, where we don't have just the intact rock, we have discontinuities. Those discontinuities, those fractures, obviously degrade the rock mass stiffness, the rock mass strength. And the reason why upscaling is quite favorable, actually, is I won't say it's impossible, but it's really not all that easy to do, to measure rock mass stiffness in the field. There are some dilatometer type approaches, but again, you're considering a rock mass that is very local around a well. These upscaling approaches that are available via models these days allow us to do things on the on the field scale. So it could be tens of miles in terms of scale. So that's probably the two definitions of upscaling that I would offer.
Thank you. Yeah, I think the reservoir engineering one is probably the one that I had less information on, and
Okay.
yeah, and it's interesting because you talk about stiffness, but there are also, when I look at in situ stress parameters around well, you can have data that's very close to the well, and you can have maybe regional data, but
yeah.
then
and of course,
missing.
You think about the in situ stress state. If you think about a fault, for example, you have damage zones where there's lots of fractures. The presence of those fractures degrades the rock mass stiffness. So processes like geomechanical upscaling can bring those two descriptions together and give you a rock mass description that, if you were to then use that rock mass description in, say, an in situ stress model, you will see some significant perturbation of that stress field because of the stiffness contrasts. So upscaling is really important. It's not just for permeability, but also for geomechanics.
Great, thank you so much. That's really helpful description and an explanation. I'm thinking that we've got 2 minutes left of the webinar, and I'm not seeing any other questions. Maybe
Great.
they might come in, or if anyone wants to say something now, it's the opportunity. Okay, so excellent. I think that's it from questions, and I'd like to thank Mark very much for answering those questions in a very detailed and informative manner. It's been great having you here and learning about modeling techniques in hot sedimentary aquifers. I think we'll close the webinar now, and thank you to our attendees for also attending.
Thank you.
Thank you both. It was great. Nice to meet you, Mark and Simran. Thanks again.
Thank you. All right.
Bye-bye.